Okay, we're gonna really start here today. So we're off to chapter 12, which seems like the first chapter we're gonna do. So why not start there? All right. We are going to talk about in this chapter chemical equilibrium. And chemical equilibrium is pretty much what this class is all about. We're going to talk about, as we mentioned last time, pretty much every type of equilibrium you never want to know about will pretty much be this class, really at the beginning. And as I said, after sort of exam two, we'll talk about some other things, but it is pretty much the big topic of the season here in this class. So let us talk about equilibrium in general and chemical equilibrium and what is happening. And chemical equilibrium really does involve a specific type of reaction that's taking place. And these are reactions that look something like this. These are reactions that have arrows heading in both directions, and these are what are referred to sometimes as reversible reactions. And chemical equilibrium revolves around these type of reactions, which are reversible. And what that means is when you see those two arrows is there is a forward direction heading from this side of the equation is called the reactants. Yeah. And going towards the products. So as we go from our reactants to our products, that is what's considered the forward part of this reaction. And what will happen in these type of reactions is eventually you will build up enough products that they will really recombine and head back in the opposite direction, where they go from products back to reactants. And that is what's referred to as the reverse direction. So sometimes people have a wrong understanding of sort of what the word chemical equilibrium means. And it's because the word has equal in it. So that means that people sometimes think that it is an equal amount of everybody on both sides of the arrow means you have reached chemical equilibrium. And it really has nothing to do with that. What it really means is at some point, it's actually the rate of the forward direction will essentially equal the rate of the reverse direction. And that is really where a system has reached chemical equilibrium. Rate, as you might remember, is kinetics, how fast or slow, right? Reactions take place. And that is really what it means when we do reach chemical equilibrium. So what does that mean? Does that mean that we have equal amounts on both sides? As I mentioned, it does not. It means that wherever everybody is in terms of their concentrations, in terms of their pressures, if you're dealing with gases, they pretty much will maintain their concentrations, their pressures at that point when they reach chemical equilibrium, because just as quick as it goes this way, it's going to come back the other way just as quick, which means everybody's pretty much going to stay locked into place as to where they're at. So again, sometimes people think, well, chemical equilibrium means I got the same amount of these guys as I do these guys, and it doesn't mean that. It's really referring to the rate of the reaction. So in this particular reaction, for example, if we reached or we started this reaction, let's say initially we started this reaction with, say, 5 molar this guy, 4 molar this guy, and nothing of these guys. And when we reach equilibrium, maybe we got 2 molar this guy, 1 molar this guy, 3 molar this guy, 4 molar this guy. I'm just making it up, obviously, these numbers. What that means is once it reaches that chemical equilibrium, it essentially they will be able to maintain those concentrations. So they'll sort of indefinitely, if you will, A will stay at 2, B will stay at 1, C will stay at 3 in my example, and so forth. So again, it doesn't mean that it is going to be equal to each other, but it means that the rate of that forward reaction will also equal that rate of reverse reaction. Now, equilibrium is also kind of interesting in a sense because if you are sort of visually looking at it, let's just say you did some reaction in a beaker and maybe it was colorless and then all of a sudden it turns red and you look at it and it just looks red now at this point and nothing much is changing. And you may look at it and go, oh, the reaction's done. There's not much happening right at this point. It went from colorless, it's now red. We're all done with the reaction. There's nothing much happening. So sometimes people think that, when it reaches chemical equilibrium, it's sort of like all done, and it's not. There is a lot of activity that's really happening. If you could like super zoom in on what's going on, if you could super zoom in on the speaker, and you would see all these guys are going from A and B, making C and D, and you got guys coming backwards, and there's a lot of activity that's happening. Even though on sort of the big level, if you will, it looks like there's not much happening, which is what it means, but it's static, it's kind of over. But there is a lot of activity that's continuing to happen to maintain, for example, like that red color that you see in there. And that's different than sort of a one-way sort of reaction, if you will, where everybody just sort of dumps out on the product side. In that case, there is nobody coming back the other way. Everything's essentially just going in a one-way direction. And when it's done, it's mostly pretty much done at that point. But in these reversible reactions, lots of activity happening, even though maybe visually to us, when we look at something, it kind of looks like it's done, but a lot of activity is still happening if you should super zoom in. Any questions on that there? So that is obviously what we just talked about on sort of the big scale there. It does look static, but again, a lot of activity happening if you were to sort of super zoom in. So if we look at this reaction where maybe we take a little bit of N2 plus some H2, making a little NH3, maybe I balance it like I'm a chemistry person here. We'll do something like that maybe. And what happens at the beginning, for example, in this reaction, pretty much what we see from this graph is that's a reactant, that's a reactant. It's pretty much all reactants. So what that means is we would expect, obviously in this case, since we only have reactants, we have really no products, that at the beginning of this reaction, the forward direction here would predominate. Yeah, so we would definitely have the forward direction predominating. And that's what we see when we look at the concentrations. We see our reactant concentrations starting to come down. And that is because you have to use your reactants to make products, right? And what we start to see in terms of our product side is, okay, we're going to start making some products that are going to happen. And we continue to see sort of a rise in our products and sort of a decrease here in our reactants as time goes on. But at some point, we are going to build up enough of these products that they are going to start to combine and head back in the reverse direction. And that's, as you can kind of see here, it gets a little less steep, the drop off there of our reactants. And also even our product sort of formation gets a little less steep in terms of how it's being made. And at some point, what we see is pretty much our reactants have flatlined, our products have flatlined, and our other reactant here has basically flatlined. And that means at that point, their concentrations here are all basically staying the same, right? There's no major change happening. And that point where they all pretty much flatline, if you will, is the point where chemical equilibrium basically has been reached. And they will maintain that way all the way through unless you do something to screw it up, which we'll talk about at the end of this chapter, stuff you could do to screw up the equilibrium. But basically, if you don't do anything to it, it will just maintain that. They'll be able to kind of maintain their concentrations all the way through. Again, because really at this point where we reach equilibrium, that is that point where we have the rate of that forward direction will equal the rate of the reverse direction. So basically, the idea there is just as quick as we sort of deplete something on the reactant side, it's going to come back from the product side, remaking them and stuff. So everybody sort of locks into place. So here, when we look at this reaction here, which is some water, a little carbon monoxide, makes some hydrogen and carbon dioxide. Initially here, we have no products. So as I mentioned earlier, just like in the last one, we would expect at that initial sort of step that we would have our forward reaction really predominating here because what affects rates of reactions, as you might remember for some kinetics conversation, are just logically thinking about it. In order for a reaction to occur, you need things to come in contact with each other, right? And obviously at this point, we have an overload of reactants because no products are present. So there's a fairly good chance that those reactants are going to come in contact with each other, and that's going to kick off, again, that forward reaction to occur. Again, at some point, we will build up enough of these guys that they will actually start coming in contact with each other. And at that point, we will get, again, our reverse reaction basically kicking off. And again, it will continue at this process, kind of like we saw in the graph there, until those rates, once again, will basically equal each other, the forward and the reverse reaction. So when you look at it graphically, that's sort of the point where you want to look at is, you want to look at your reactants line, your products line, and at some point, in this case, they actually overlap, but they oftentimes won't. But where they both basically flatline, that means that they are able to maintain their equilibrium. All right, so let's take a look at this one a little closer, this reaction here. If we have this reaction and we add more H2O to this flask, what's going to happen to the concentrations of everybody else? So take a moment, think about if we have this reaction that's at equilibrium, and then we add some more H2O to this flask, what should happen in terms of all the other reactants and products? Should they go up? Should they go down? Will they stay the same? So take a moment, kind of think about it here, and then we'll kind of. Okay, so let's take a look. So we have this system. So essentially, we have this system in equilibrium. So we got a little bit of everybody, in the beaker or wherever it may be, the container that's going on. So if I add more water to this, let's start with the CO here. Will the CO's concentration, will it stay the same? Will it go up? Will it go down? What should happen? So I hear up, I hear stay the same. The only one I do not hear is the correct answer, which is if I add more water, right? That means water is going to have a pretty much easier time, right, to find some CO because there's just more of it, right? Some presence of more of it is going to allow it to really react with the CO probably at a greater rate than anybody else. And what happens when the water and the CO start to react? Does the forward reaction occur? The reverse reaction occur? Which reaction should occur? The forward one, right? So that's going to pressure, basically in this case, by adding the water, that's going to cause our forward direction here basically to kick out or kick off. And the result of that is obviously we're going to use these two guys to make products, which means the concentration of CO in this case should actually go down, right? Because we need both of those things to make products, right? So cleared, if we needed to make products, we're going to use some of it up and it should go down. That would mean over here on our H2 and CO2 side, concentration of those guys should then go up, right? Because we're now making products, right? So we should expect these guys to kick up, right, in terms of their concentration from where they started. Now, how about our friend water here? What's going to happen with water? It is ultimately going to go down, right? But first, it's going to actually go up. And that's because you added it, right? So clearly its concentration went up. But once it starts reacting with CO, it then should make its way back down, right? So it should work its way back down. Now, in the case of water, if you actually had numbers, you might actually see water will actually end up maybe higher than it started with, maybe. And that's only because you added it, right? And that's the reason of that. But really, overall, what's going to happen is it should actually work its way back down as it's reacting with CO. So we'll get kind of an artificial increase only because we added it, but then it should start working its way back down. Any questions on that there? All right, then let's take a look at this one again. But in this case, we're going to add a little H2 to this equilibrium. What's going to happen to everybody else in that reaction? So take a moment and think about it here. All right, so let's take a look at this. Now we're adding H2, which is frankly over here. So we'll start with CO2. What's happened to CO2? it should go down. And because of the addition of H2 in this case, that should kick off the forward reaction and the reverse reaction. It should kick off the reverse reaction here. Again, for the same idea, we now have a sort of a plentiful of H2 there, right? Which means it's not going to have a hard time finding some CO2 to start to react with. And once again, that will kick off our reverse reaction basically happening in this case. And that would mean in the case of this example here, the water and the CO should again go up, right? Because we have our reverse reaction basically happening in this case. Now, in the case of the H2 here, we'll see probably something similar to what we saw with the water. We will probably see it, in the case of H2, start to spike upwards. But once it starts reacting with the CO2 again, it should work itself sort of back down as it's going to be used up to make our reactants in this case, as the reverse reaction is basically happening. Any questions on that there? Okay. I think we took a look at that one earlier. So let's talk about the equilibrium constant and its applications. So if we have this reaction, for example, here, N2O4 goes to 2NO2, we can write a relationship for this, which is known as capital K. And I say capital K because lowercase k is the rate constant from kinetics. Yeah, so capital K here is what you want to use. Also, that is the letter that brings you Chem 200B is brought to you by the letter K, as you will see it in every situation imaginable. K is the equilibrium constant. And essentially, the way that we calculate K is we basically take the concentration of our products divided by the concentration of our reactants. Now, typically when we use these brackets, that means concentration. And that is everybody's favorite concentration usually, which is molarity, right? Which is moles per liter, right? So that is molarity, which is moles per liter. Now, when we do this, it gives us a relationship that is, as the name implies, constant. Yeah. So the equilibrium constant is a constant value. The only thing that will ever affect the actual value of the equilibrium constant is temperature. So it is specific for the reaction the way it's written, and it's also specific for that temperature that you're talking about, but it will give you always a same number or constant value. We also need to take into account everybody else's favorite thing, which is like, the mole-to-mole relationship, little stoichiometry action, the coefficients. So we do take the concentration to the coefficients. So that is where the 2 comes from. Here, there is no coefficient, which is 1, and that is basically what that is right there. So in general, if you have an equilibrium constant, you take the products concentrations to their coefficients in the balanced equation divided by the reactants to its concentration. After being beat into your head through so many chemistry classes of units, frankly, there are no units associated with K. So most people do not use units per K. It is just an actual number. So let's talk a little bit about the number. K is typically just a number. So if I have a large value of K, that would mean when I reach equilibrium, would I mainly expect to have more reactants, more products, or the same amount of it? I should have more products. And just mathematically thinking about it, if you divide a large number by a small number, you get a large number, right? So it would mean that when you reach equilibrium, you mainly have products. And vice versa, if you have a small value of K, that means that you would mainly expect to see reactants when you reach equilibrium. Now, there is, as we'll talk about, degrees of small and large. You could have a really large number, you could have a really small number, and any sort of variation there in between. By the way, if we have like a K value of 1, you sort of have equal amounts pretty much, right, of each of those things. So pretty close to equal amounts of products are reactants in this case. Any questions on that there? Now, one concept about the equilibrium constant that people always have a very hard time sort of understanding is the idea that you could start a reaction that's a reversible reaction like this, and as long as you keep the temperature constant, you could start with all reactants and calculate the equilibrium constant. You could start with all products and calculate the equilibrium constant when it reaches equilibrium. You could start with a little bit of products, a little bit of reactants, let it reach equilibrium. It will always give you the same ratio of products to reactants. You will have the same value of K. Sometimes people think, well, in this experiment, I did a lot more of these reactants than I did in the previous one. I should get a different K value. Or I started with some products that I didn't have in this one. I should get a different K value. As long as you keep the temperature the same, you will end up with the same proportion of products to reactants. It doesn't matter how much of these things you start with, as long as the temperature doesn't change. So you may say, how's that work? So let's just take a basic math example, which we're going to try to do here late in the week, but we'll try here. So if I take 8/4, for example, which is the ratio, say products to reactants, what's the number I get? 2. Yeah. Take a ratio of 4 to 2, and I divide it. What do I get? 2. Take a ratio of 2 to 1. What do I get? Those are all different ratios of stuff, right? And they all end up at the same number, right? And that's the same idea here. You can start with as much as you want of all these things. Once you may have different numbers at the end, you started with different amounts, but the ratio of those products to the reactants, as long as you don't change the temperature, will always end up being the same number. Any questions on that there? So when we talk about the temperature affecting the value of K, why don't we talk a little bit about what that means? So what that means is, let's just say I did this reaction. This was my ratios here on the left, and I did it at 25 degrees Celsius. And again, no matter how I started or did the reactions, I ended up with the same number all the way through. And if I did this exact same reactions, and maybe I did it at 50 degrees Celsius, maybe I will get an equilibrium constant, say, of 4 versus 2. And what that means is the comparison of what the equilibrium constant is at 25 degrees to what it will be at 50 degrees, they will be different numbers. But if I did 4 more experiments at 50 degrees and I kept them all different amounts of starting materials, ending materials, all 4 of those experiments that I do, the K value should end up at what number in my example? 4, yeah? So we'll stay at 4 as long as you keep it at 50 degrees and do a bunch of experiments. So when we talk about the equilibrium constant value changing with temperature, it's a comparison of 2 different temperatures. You'll get 2 different K values. But again, if you stay at the higher temperature and do a bunch of experiments, you should expect the same K value all the way through. If you at a lower temperature, do a bunch of different experiments, you should expect the same K value. But they will be different upon comparison of, say, the higher temperature and the lower temperature. Any questions on that there? I was going to end with I think, but that doesn't seem right to say. All right. So here's same idea with our equilibrium constant in case you like different letters as well. I will say here, I'll just jump the gun a little bit, but another one, we'll talk about it in the right spot. What is a large value? What is a small value? Well, it is that big value of 1. So anything considered with a K value above 1 is considered a large value of K, and you would expect mainly products when you reach equilibrium. Anything that is less than 1 is considered a small value of K. So as I mentioned before, there is sort of a big range of that. We will see some equilibrium constants where you have it to like times 10 to the 54, right? And we may see some equilibrium constants where you have it like times 10 to the minus 36, which is a super small number. And again, there's K values anywhere in between. As I mentioned before, as your K value sort of gets close to 1, you may have sort of equal amounts, or there'll be a very slight difference. So it may go one way or the other in terms of, to the left or right in terms of products or reactants. But definitely, if you have anything greater than 1, considered large, and anything less than 1, considered small. So here, for example, we have Mickey at the start of the day, reacts with a couple of these guys. Mickey at the end of the day, upside down. And we get a K value here of 25. Thank you for not laughing at all at that joke. That's all right. K value 25. That means that when we reach equilibrium, we should mainly expect some reactants or products. I'll just entertain myself. It's okay. Reactants, products, what should we have here? It's a 50-50 shot. You can only be wrong, I would say, only once, but I guess if you guess the same thing twice, you can be wrong twice. We should mainly have products. Yeah, so a K value here of 25 would be considered large, which means we would expect mainly products when we reach equilibrium. Now, there is certain degrees of this, as I mentioned before, and even in like super large values of K, would I technically still have reactants? You would, even though it would be probably mostly, if you had a super really large value of K, it would mostly be considered in a lot of cases a one-way street, but it is always still a reversible reaction, which means even a little bit of it will head back the other way. So sometimes when people see a really large value, or for example, even a really small value, they assume, oh, well, it must just kind of be a one-way street, one way or the other. But always when you have a reversible reaction like this, even in those extremes, there is still a small amount going back the other direction because it ultimately is reversible. Even though some people may consider it kind of a one-way street, you always have that little bit coming back. And we'll do some calculations later on in this class where that's the case. Like you end up with, for example, in a really large value case of an equilibrium constant, you end up with a concentration of one of your reactants of like times 10 to the minus 18, right? And that's essentially not very much there at all, and pretty much nothing there, but technically a smidge of it is still technically there. And it's the same idea when you think about things that we'll talk about as well in terms of solubility and solubility rules, right? Things that are insoluble, things like silver chloride, we think of maybe just as a one-way street. But even silver chloride, which technically based on solubility rules we were taught is insoluble, will be a little bit soluble in certain situations. There'll be a little bit of it that will break apart. So even though you may hit some extremes with an equilibrium constant, it is always still a reversible reaction. And you always still have a little bit of the other way happening, even if it's really, really small. Any questions on that? All right, so let's talk a little bit about homogeneous equilibrium. And homogeneous equilibrium makes me think of homogeneous mixture, which also makes you think of it is the same throughout, I think. Yes? Isn't that what homogeneous mixture means? I think so. I taught it last week, I hope. And that is what it means. And what it means here when we talk about a homogeneous equilibrium is everybody is in the same phase. So in this case, they're all gases. All the reactants, all the products are gases. So we can write our equilibrium expression like normal, our concentration of our products, again with the coefficient, divided by the concentration of our reactants. But when we deal with gases, we oftentimes deal with our friend pressure, right? A little PV equals nRT action. That is the ideal gas law. Yeah. By the way, when you use the ideal gas law, pressure should be one unit. It should be ATM, right? Volume should be. That's good. I like it. And which is moles should be. I like it. Moles. Yeah, seems good. Temperature should always probably be Kelvin. Yep. And that's a 273 edition, right? To convert to Kelvin. Yeah. from Celsius. And R is our gas constant, whatever value you learned. People that took me learned this value because it's the one stuck in my head, but a lot of people use 0.0821 these days and stuff like that. So we could actually write an equilibrium expression that actually deals with pressures, and we do it basically the same way. We take the partial pressure, which is what this is, partial pressure squared for the coefficient. So we still need to square it because of the coefficient of our products, which is NO2 in this case, divided by the partial pressure there of our reactants, which again is to the first power because of the coefficient. These are two of our first of 32 K values. This is sometimes referred to as Kc. I'm going to go with concentration because that starts with C. That seems good. And that is the K value that you use your concentrations for, your molarity for. I'm going to go out on a limb here and go with Kp as pressure there. So Kp value is the equilibrium constant when you are dealing with pressures. In most cases, the Kc and the Kp value do not equal the same numerical value, although it is possible they could, but in a lot of cases, they will not equal the same actual number. But they will tell you the same thing. And what I mean by that is if you have a large Kc value, like we talked about, you would expect mainly products at equilibrium. If you have a large Kp value, you would also expect mainly products at equilibrium. And vice versa. If you have small values for each of those, you would expect mainly reactants. It works the same way because if we have mainly products at equilibrium, what causes pressure? Something needs to hit things, right? So if you have a lot of products that are gases, that means they're probably colliding a lot more than the reactants that you have less of, right? And they're causing more pressure, which translates to a greater Kp value in that case. And vice versa, if you have less products but more reactants, they would be flying around a lot more and colliding a lot more, causing a lot more pressure, and you would have a much smaller Kp value. So the K value, and this is also something you should keep in mind as we go through these chapters, is there a tremendous difference in sense of a Kc, a Kp? Are they really different things? They are not. They're equilibrium values. So it doesn't really matter. We'll see Kc, Kp, Kw, Ksp, Ka, Kb. I know you think I'm kidding. Kf. I'll keep going. But we'll see all kinds of K values, and they're really all the same thing. They're really all just the ratio of the products to the reactants. It just depends on what you're using. Molarity over molarity, pressure over pressure. I will say in the case of pressure, and it may not make a lot of sense right now as we're talking about a little bit later on in this chapter, it will hopefully. Typically speaking, when you do true equilibrium type of problems, not really like what we're looking at right now, but later on when we do the heart of equilibrium calculations, if you have pressures, you should usually get them into atmospheres when you're doing the actual equilibrium calculation that we'll talk about a little bit later on in the chapter. And sometimes people are given stuff in different pressure units like millimeters of mercury, right, or torr, and they want the answer in those units, and they go, okay, cool, I could just like leave them in those units. It's okay. But typically, when you do a true equilibrium calculation, we're going to do a little bit later on in this chapter, you do have to kind of convert them into atmospheres before you do it, and then reconvert them at the end. By the way, the conversion between atmospheres and millimeters of mercury and torr is 760. Yeah. So again, not really crucial at this point as we're going through these sort of chapter here, but a little bit later on in this chapter, I'll point it out again where it really is crucial that you do get everybody into atmospheres. So speaking of this, we may have a situation where maybe you're given the Kp value, or maybe you're given the Kc value, or you have enough information to calculate one or the other, and maybe you're interested in the opposite value. So maybe you have enough information to calculate the Kp, but you really want the Kc value, or you have enough information to calculate the Kc, but you want the Kp value. So of course it's chemistry, so there is going to be an equation that allows you to go between those two things And that's what's in the box. And again, a reminder, you are responsible for formulas and stuff, so make sure that you do know them. The Kp value equals the Kc value times RT, and R is our gas constant right there. It is this version of it. T is obviously our temperature in Kelvin, like normal. Delta N is the change in the number of moles of gases that you have. And that is the moles of the products that are gases minus the moles of the reactants that are gases. And that's really important that you do it that way. So for example, let's just say I had this. What is delta N in this case? 1? Anybody else? Well, let's see. It is the difference between the moles of the product gases and the reactant gases. Simplest way to figure out the moles is the number in front, right? So on my product side, I have how many moles of B? 1. Yes, right here, coefficient. And on my reactant side, I have delta N is -1 or -1 in this case. Does it matter mathematically? It does, because if you look at this equation, just the back part of it, if my delta N is 1, I'm doing nothing to it basically, right? It's just going to be that. But if my delta N is -1, that is the reciprocal, right? So you got to do 1 over it. So it does make a really big difference here. And sometimes people will just take the difference, but you want to make sure that you do products minus reactants, because if you do get a negative, it is going to affect the math part of the calculation that you would have to do. So it's really important to make sure that you don't just disregard the negative, which is a common error that sometimes people make. Any questions on that there? All right. Now, in a homogeneous equilibrium, if we look at this guy here, which is a little acetic acid plus some water, making some acetate and some hydronium ion. And if we write the equilibrium expression like we were talking about, and we take our products over our reactants, we'll end up with something that looks like this. But in this reaction, pretty much water's concentration, because it's a pure liquid and there's so much of it, pretty much stays constant, which means in reality, we should not include it in our equilibrium expression. And the proper equilibrium expression for this reaction should actually be this, which is our products, our acetate times our hydronium ion, divided by the acetic acid, and you should not include the water or the pure liquid. So in general, we don't have any units, and I'm just going to scratch that out basically because it's constant. So if you were to write the proper equilibrium expression, that is what it should look like right there. In general, there are two things that we do not include when we write the equilibrium expression. So I'll just kind of jump the gun a little bit here. We do not include, as we see here, we do not include anything that is a pure liquid, because frankly, it stays pretty constant throughout. So there's lots of water in water. Its concentration really doesn't change all that much. The other thing that we do not include is anything that is a solid. And that is frankly because if it is a solid like my calculator and I throw it into my beaker, not much is going to happen with it other than it's going to like sink to the bottom, right? In order for it to do something, if it's in like a beaker of water, it has to actually dissolve, right? And that's really will allow it to interact. But in the solid form, it's not going to do much. I hope I didn't break the calculator. I might need that one day. All right. So what do you include? Well, it pretty much just leaves two things. What you do include in your equilibrium expression is anything that is aqueous and anything that is a gas. So those are the two things that should end up in an equilibrium constant expression. Anything that is a liquid or solid, basically you leave out because they're not really participating all that much in the equilibrium and their concentrations are not changing too much. By the way, when we talk about ions, right? Where do we typically find ions? Yeah, we typically find ions in solutions, right? And that's what aqueous means, right? It means a water environment. That is where ions are, right? They're surrounded by water molecules. They're floating around, no bonds to break. They're good to go, right? To react, which is why they're important, obviously, in equilibrium, because frankly, they're good to go as they're floating around. They're ready to react. Gas molecules as well, right? They have a lot of energy. They're flying around. One thing you need for a reaction to take place, right? As you might remember, or maybe not, because they don't teach that anymore, is that they need to come in contact with each other and they need the right amount of energy, right, for a reaction to really take place. So clearly, if something's in the gas state, it's moving around a lot and it has a lot of energy, which means when they collide, good chance it's going to kind of do something and affect the equilibrium. So that's why those two things really are part of the equilibrium expression. Questions on that? As I mentioned before, just a number, no units. Now, you should also remember, though, that you will be asked in some problems not necessarily to solve for the equilibrium constant, but you may be asked to solve for a concentration or a pressure, and those things do need units. So typically, if you solve for something that's a concentration, molarity is probably your unit. And a lot of times, again, as I mentioned before, atmospheres or some unit of pressure if you're solving for some type of pressure. So solving for K, no units needed, but you oftentimes also will be solving for those things. So you need to include the units when you have those. All right, so take a shot at these two here. We're looking for the Kc and Kp expression if possible. Take a moment or two, see what you come up with. Okay, let's take a look. So we'll start with the first one here. We can write our Kc. And once again, we're going to do the concentration of our products, which in this case is NO2. We do need to take it to the fourth power there because of the coefficient. We would then times it by the concentration of O2. Its coefficient really is 1. So much like in most cases in chemistry, you don't need to put the 1. We'll divide it by the concentration of HF. And do I include, I should do the right one, I suppose. So maybe we won't divide it by HF. And I'll look at the one we were actually doing. There you go. We're going to go over here to this reactant, which makes more sense. So we're going to divide it by the concentration of N2O5. And we will also square it there because of the coefficient. Any question on that one there? Can I write a Kp for this one? I can because there's all gases there. So the Kp will look pretty much the same deal, except instead of concentrations here, we're going to do partial pressures. So we'll take the partial pressure here of NO2. Once again, we do need to take it to the fourth power because of the coefficient. We'll times it by the partial pressure there of O2, which is to the first, and divided by the partial pressure squared of N2O5 in this case. Any questions on either of those there? Looking at the second one here, we'll do our Kc. That would be the concentration of our H3O plus times the concentration of our F minus divided by the concentration of HF. And now I'll ask the question, since we're actually on this one, do I put the water in? I do not, because it's a pure liquid, so we do not put it in. What happens if my water is steam in the gas state? Do I put it in? I do, because it's a gas, so it will participate, right? So it's flying around like all the other gas molecules, right? Water vapor, basically. So you would include it, but again, here, because it's liquid water, pure liquid, you would not include it. How about Kp for the bottom one? Yeah, there's no gases, so no pressure. So you kind of need gases to do that. I would say in most cases, you'll probably see them all be gas, or you might have like a solid maybe decomposing into some gases and stuff like that. What happens if I have something like this? We'll do this as a gas. That's a really bad G. Just imagine that's a G. What would be my equilibrium expression for this one? You actually could, because you do have products, right? So the K here would be the concentration of B squared, and that would be the Kc. You could also write a Kp for this, which would be the partial pressure there of B squared. We can find that thing here. Oops. So you would have the partial pressure squared of B. So obviously the reactants here would be basically 1, right? And like normally, and when you write fractions, if you have a 1 on the bottom, you don't really put anything there, right? You just kind of leave it off, and that's technically what it would be. But if I had this, if I had, I don't know, we'll just do something like this. What would the equilibrium expression look like here? A squared. It would be, yeah. So it would be basically 1, since we have nothing on the product side, over A squared. So it would look something like that. Any questions on that? So it's possible you could have just products that would be included. It is possible you could have just reactants that are included in the equilibrium expression. And again, if it's just a reactants, you kind of do the same thing, just put 1 for the products over whatever the reactants are, basically. Any questions on writing equilibrium expressions there? Okay. All right, that's not bad. All right, so why don't we try one here? Some calculations here. The equilibrium concentration for the reaction, there it is, that we got here with carbon monoxide and a little chlorine. Gives us concentration at equilibrium of 0.012, 0.054, and 0.14. Calculate both the Kc and Kp value here for each of these. So take a few moments here, grab a calculator, see what you come up with. I'll give it a go. Okay, let's take a look, see how you're doing. So in this case, we're looking for both the Kc and the Kp value for this reaction. Which one would make the most sense to solve for first? Yeah, because we have concentration, so that would make the most sense. We have nothing to do, we have nothing given to us about pressures, so that's probably not a good place to start. So we would want to start maybe with our Kc expression here. And again, we're going to take our products, which in this case is our COCl2. Coefficient is 1 divided by our CO, where coefficient is also 1, and the Cl2 there. And these are equilibrium concentrations, which, by the way, is what you need to go into an equilibrium constant, right? They has to be equilibrium concentrations. They cannot be initial concentrations or anything like that to go into that. So we're going to put everybody in the right spot there. So we're going to go, I think, 0.14 there up on top. A little CO there, 0.012 and 0.054. Gonna pop that all into the handy dandy calculator there. Make sure perhaps you take 0.14 divided by 0.012, hit equals, divided by 0.054 and hit equals. Try not to put too much into your calculator all at once unless you know what you're doing. You get a like a 216 there on the calculator, but you're good chemistry students, so you're gonna lay up a 220 maybe for significant figure purposes. As you want to do those things. Any questions on that there? Everybody there in that calculation is 2 sig figs, right? So you got a little significant figures. I feel like I'm teaching chemistry. I should say something about that. Good talk. All right. This is our Kc value. That's going to be good because now we could use, right, our formula there to convert from Kc into Kp action. And I think it is the Kp is equal to the Kc, a little RT delta N action happening. So let's start with our delta N in this case. Is going to be our products, which is 1, right? Minus our reactants, which is 1 and 2 in terms of the coefficients. That means we have, again here important, a -1, right, for our delta N. And again, that negative is obviously important in our calculation. R is our normal gas constant there, 0.08206. Or if you want to use 0.0821, you can as well. Our temperature, we do need to convert to Kelvin. So that's a 74 plus a 273 to convert that to Kelvin. Looks like a 347. And I think now we're good with everything that we need. Our KP in this case would equal, depending on which number you use, we'll go with the rounded number, why not, to 220, 0.08206 times our 347, and again to the -1, not just 1. You want to clean up what's in the parentheses there first, a little 0.08206 action times 347 hit equals, take 1 divided by that answer. That's doing the reciprocal there, right? Gonna get you a 220 and like a 0.035118747 on your calculator. Gonna times it by a 220. Gonna get us a KP value here of 7.7 or 7.6 if you didn't round to 220, I suppose. Yes. Any questions on that there? So this is a situation like we were talking about earlier here. Clearly, we have enough information to get us to the KC value. So that does make sense to do it. And then using obviously that formula, we can also relate it to the KP value. These are small or large values of K. They are large, which means when we reach equilibrium, we should mainly expect reactants or products. Once again, here we see that, as we talked about earlier, the Kc and Kp value are not numerically the same value. Again, they can be, but not usually. But they both, again, tell us they both would be considered large values. So they both, again, tell us the same thing, that we mainly would expect products when we reach equilibrium. Any questions on where any numbers came from? Yeah. How to calculate? Yeah, it's so the delta N is the moles of your products minus the moles of your reactants. So the easy way to do it is just look at the coefficients in the equation. So we go to our product side, which is over here. Coefficient basically is 1, and we would subtract it from our reactant side. And again, this guy is a coefficient of 1. This one's a coefficient of 1. So basically we got 1 plus 1, which would give us 1 minus 2. And that's how we get to the minus 1. Yeah. So remember the coefficients, right? When you did stoichiometry, is the mole to mole relationship, right? So that is basically the moles of what you got going on in those cases. Other questions? Let's try another one here. I don't think you, I think you have NO on both of these. So let's go with the first one here as NO2. That might make it easier to solve. So here we're actually looking for a equilibrium. All right, let's take a look. So a couple things we want to just think about logically, right? I see a KP value given to me. I got some pressures. I'm looking for pressures. So clearly KP is the direction here we should obviously go with. So that's probably a good place to start, is to just write the KP expression here for the equation. So remember, the KP is really no different than the KC, other than you're dealing with pressures, but it is always, when it's an equilibrium, products over reactants. So we'll take the partial pressure there squared of NO, which is our product, times the partial pressure of our O2. Here again, the O2 has a coefficient of 1, so we don't have to worry about any type of squaring or anything like that. We are going to divide it by the partial pressure here of our NO2, which we do need to square once again because of the coefficient that we got going on there. That actually is going to equal here a 158 in terms of our KP value that was given to us here in the problem. We do have the partial pressure at equilibrium of NO2, which is 0.4 atmospheres. We also have the partial pressure there of NO, which is 0.27 atmospheres. And we're looking for this, guys. So we could pop our numbers in there. So really that is NO2, which is going to go up on top. So we're going to go 0.4, and we are going to square it. That will be times the partial pressure of O2 divided by our NO. I think I popped that in the wrong spot, so let me put it in the right spot. I apologize. There we go. That's NO up on top. That's that guy. So let's go with that guy there, 0.27 squared, divided by our NO2, which is on the bottom. Now we'll put that guy there. There we go. And we're going to square it, and it will equal 158. Mathematically here to solve this, we're going to basically multiply this to the other side, right? And then come back and divide that afterwards, however you want to do that. So if we want to just kind of get some numbers, we can. 0.27 squared is going to give us 0.0729 partial pressure of O2 divided by 0.4 squared gives us 0.16, and that will equal our 158. So we'll multiply that 0.16 to the other side. And we'll take 158 times 0.16. Looks like it is 2528. We're then going to divide this now to the other side. We multiplied that. And at this point, that will give us our partial pressure of O2, which should be about 346.7. We will probably go to maybe 3 sig figs, as it looks like all these guys are 3 sig figs, basically. So that would take us to here. We do a little rounding, maybe like a 347 atmospheres, yeah. In that case. We do need units here, right? Because that's a pressure, so it should be the same units as everybody else. Question on that calculation. By the way, Kp value of 158 is small or large? Large. So we would mainly expect what at equilibrium? Right. And that's quite reflective in the partial pressure there of oxygen at 347. That's a huge amount of pressure. So clearly there's a lot of it flying around causing collisions, right? Any questions on any of that calculation? Yeah.
How would I know?
Yeah, so the other one is a situation where you have one or the other sort of piece of information given. So either you're able to, or you're given the KP or KC, either you're able to calculate it or it's given to you, and you want to find the opposite guy. That's when you would use that. So like in the previous problem, they wanted both the KC and the KP, right? But we were given enough information to calculate the KC. So the only way, based on the information given to us, that we would ever be able to figure out what the KP value was in the previous example is to use that equation, because we have no information about pressures or anything like that. So we can't calculate directly. Here, we're able to calculate directly the KP if we wanted to, or use it because we have pressures and we also have the KP value given to us. So that previous equation would be a problem like this, where maybe you're given enough information to get the KC, but you really need the KP, and you would use that formula to switch it over, or vice versa. Other questions? Why are we dividing? I'm sorry, which step? Here? Yeah, so mathematically what we would be doing, which is what we did here and then here, is first you would have to multiply what's on the bottom to the other side, and then you would have to come back and divide by what's on top, which is what we did here. So you have to kind of do those steps, first multiply and then divide. Yeah. So remember math, and pretty much when you have the equal sign, you always do the opposite of where things are, right? So since this is technically on the bottom, you're like dividing by it on the left. So to get rid of it to the right, you need to multiply, do the opposite sort of formula. These two guys are technically multiplying. So to get rid of this, you have to do the opposite and divide it to the other side. And so that's what we're doing. So that was just the order of the math in that step too. It is this guy squared. Yeah, yeah. And then this guy on the bottom is this guy squared. Yep, yep, yeah. it really has nothing to do with this type of calculation. It's just telling you at that particular temperature, that would be the equilibrium constant for that reaction. Yeah. So it's kind of sometimes like extra information you don't really need in that sucker calculation. Other questions? All right, let's lay it up